For this video, let us try to illustrate the process of dividing complex numbers. And we are also going to introduce here the idea of conjugate, because it's very important as we simplify the result or the quotient. Let's introduce two complex numbers. Let's say z sub 1 be a plus bi, and then z sub 2 be c plus di. Again, the real part of your z for both of them are the coefficients a and b. A and c rather. And for your imaginary part of your z's are the coefficients b and d, which will be multiplied with your I equal to the square root of negative 1. Okay, so it's very important to emphasize that, because later on we might use some illustrations later. Now, for a division of our complex numbers, let's say z sub 1 over z sub 2, it's very important that here it's where z sub 2 can no longer be 0. Okay, so now let's illustrate z sub 1 to be divided by z sub 2 using the given illustration or representation. You have a plus bi over c plus di. Next question here is, how can we get the quotient of these two, where commonly complex numbers are expressed in their forms? This is where we are tasked to make sure that our denominator will no longer contain your I. In short, we're going to multiply certain expression in such a way that the I there will be simplified. And that means we're going to introduce here the concept of complex conjugate. Similar to rationalizing denominators, the goal is to remove or, not necessarily remove, simplify any radical expressions in our denominator. Here, since we would like to simplify any I in our denominator, we're going to have conjugate. The conjugate of a number, let's say, generally, because we will have here a plus bi, let us say x plus yi, its complex conjugate is still a binomial expression. Okay, where we have the first term, same second term, but the operation is opposite. This is true both ways, so that once you multiply them, you will get here, according to the difference of two squares, x squared, and you have the square of yi, and then you have here minus here, which will yield a result of x squared minus y squared and then I squared. And we know that I is square root of negative 1. When we have I squared, so you take the square root of that, and you will get here negative 1. In short, this will be further equal to x squared minus y squared times negative 1, which will give us x squared plus y squared. As you see here, we don't have i's. That means that whatever be the result of this would be real number, and if that would be the case, our denominator, when duplicated here, will be real number now. So in short, we are going to use that in dividing this, so that we could have an expression which is easier to look at. So let me rewrite it here. Take note that our z sub 1 over z sub 2, as represented earlier, was a plus bi over c plus di. Take note that it's the denominator we're trying to simplify. Hence, we're going to look for the conjugate of our denominator. Take note of this. It would be c, same first term, same second term, but opposite in sign operating them. Take note that what we're multiplying here is just equal to 1. That would mean it would be the same expression on our numerator. So we're multiplying that, and this is just again equal to 1. So we're multiplying 1 to the entire expression. We are not necessarily changing the value of that. So with that here, this would mean this is actually equal to a plus bi, c minus di, and for our denominator would be c plus di times c minus di, which our denominator would, again, similar to what happened here, you will have c squared and then minus di squared, or further c squared minus d squared I squared, which is again equal to negative 1. So c squared minus d times negative 1, that's d squared, which will give us c squared plus d squared, a real value. That's for our denominator alone. And we are done trying to simplify that. But of course, our numerator is still like that. So let's simplify that further. So using FOIL method here, you will have AC. Using the FOIL method for our numerator, take out of that, minus ADI plus BCI, then minus BDI squared, because that's BI times DI. All over, you can use this now, C squared plus D squared. So, you will have here AC, factoring the negative, I'm just going to rearrange this first, BCI minus ADI, and again, this is minus BD times negative 1, as mentioned, because that's the square of your negative, your I. So that would mean you have here, these are all over C squared plus D squared. So we have here AC, this becomes plus BD, and then, sorry for this one here, now this time we're going to factor out I for these two. So you will have here plus BC minus ADI all over C squared plus, D squared. Or you can also group this if you would like to. And this is actually the result when we try to divide complex numbers. So this is, if you can memorize that or be familiar with that, automatically you can apply this automatic formula in dividing two complex numbers, noting that these are the actual representations. Or you can also try the longer method to make it more comprehensive. We'll have an example for this in the next video together with the rest of the operations. So please be guided with that. But this is how we illustrate division of complex numbers. Important thing to remind ourselves that our denominator should not be equal to 0, and the existence of complex conjugate. Thank you very much for watching.